Well, good morning and welcome to this webinar. Today we're going to be talking about Java, microservices and Docker and how we can use the Zing JVM from Azure to improve performance and make your microservices work in a way which is going to be better for the types of applications you're developing. My name is Simon Ritter. I work as the Deputy CTO at Azure Systems. So what I'd like to do is, first of all, start with just a little bit of a discussion around microservices and Docker in general, and then we'll move on to talking about how we use Java specifically, and then how Zing can help with some of the issues that you might be facing when deploying Java-based microservices, especially with Docker. So the first thing to understand is about the ideas behind microservices. They've become very popular in the last 18 months, 2 years. But fundamentally, there's nothing really that new about what microservices are. It's really about distributed computing. And I think it's really important when you're considering an architecture like this for application development to understand that distributed computing has been around for a long time. There have been many different attempts at solving the problems of distributed computing. And so when you're thinking about using this type of architecture, you should think very carefully about whether it really does make sense from the point of view of the advantages that you get versus some of the things that you will have to solve as different problems. So distributed computing means that you have to be able to locate services. It means you have to be able to position services where you want for load balancing. You need to have reliability, you need to have network connectivity, all sorts of things around that. So it's well worth considering whether those are things which are detrimental to your application versus the advantages that you get from using microservices in your application. Now, one of the things that's worth looking at as well is why have microservices become so popular in the last, as I say, 18 months to 2 years? And really, the first thing which has caused a rise in the popularity of this idea is the different approach that people have in terms of the methodology that they want to use for developing software. Agile methodologies are now very much in favor for development. The reason for this is that people want to move away from having very big releases which are separated by long periods of time. So clients have to wait a long time for new features that they want in software. What people want to be able to do is have a more agile methodology, a more agile way of responding to the requirements of the business, of their customers. The idea behind this is that rather than waiting until a big release, which could be many months, even years between releases, what we want to be able to do is to deliver features when they're ready. So we create new features, we construct them, we build them, test them, and when they're ready, they are deployed. And that can be independent of other features. So it allows us to roll out new features much more quickly and enable people to get the services that they need. Now that's also been tied into the rise in what we call DevOps. And this is where we're seeing really the sort of distinction between a development team and an operations team being reduced. Traditionally, what would happen is the development team would be given a set of requirements, they would develop the software, they would create a big piece of software for deployment, and then they would hand that off to the operations team. The operations team would be tasked with deciding how to deploy that application, what hardware to use, how to deploy clustering, how to deploy load balancing, all of those types of things. But as I say, what we've seen is much more of a shift so that developers now, in using an agile methodology, are taking more of the role that would be traditionally an operations role. When you build an application, you build it, you use continuous integration, so you're rolling out the changes, compiling it, deploying it to the system that's going to be used. Because of the rise in cloud computing and the popularity of cloud computing, it means that you don't need to necessarily have dedicated staff who will say, right, we're going to put these machines in the data center, we're going to configure them with this operating system, we're going to have this app server, and so on. much more easy to deploy into the cloud. You simply take your application, your jar file, your components, and you can deploy them directly into the cloud using automation tools. And that's really the third piece, is the tooling which enables you to do that automatically. Continuous integration, continuous deployment, things like Jenkins, things like Hudson, things like Chef, Puppet, that enable the automation of deployment of these types of microservices. So it's these things which have really caused the rise in popularity. Agile methodology, the shift towards DevOps and away from having separate developers and operations staff, and the tooling that allows us to automate these things. If we look at how microservices work, it's about dividing. So what we want to do is to separate out the monolithic application that we traditionally have into a number of discrete services. And the idea behind this is to do one thing and to do it well. That's the kind of catchphrase that's used when talking about microservices. Each individual service can be developed in isolation. It can be developed according to a particular interface so that anybody who wants to use that interface knows exactly how to communicate with it, how to send data, how to receive data from it. But it's the idea of breaking up monolithic applications into smaller, discrete components that can then be joined together to deliver the services that people actually require. And if we look at that in a little bit more detail, what we can see is that we have our cloud architecture. We have one cloud which is going to be our persistence of our data in some sort of database, and then we have a number of services, microservices, which are going to deliver the facilities that our end users want. Now, from the end user perspective, there is no difference. All they are going to see is potentially a web-based application. They will go to a website, they will interact with that application. How that application is actually implemented behind the scenes doesn't matter to them. All they're interested in is, does the application deliver the facilities and the services that they actually require? Underneath, what we have is a number of microservices. And the advantage here, as I say, is to have each service doing one thing and doing it well. But we can then also divide things up, so we can say, right, we want to link these different services together. We'll have each individual service providing different parts of the overall application and then working together to deliver that particular functionality. Our development teams can then be broken up so that we could have one development team for each service. We could have one development team that takes care of a number of services. But again, we can focus the expertise for a particular type of service into that development team. And then a different development team could be responsible for different services within our overall architecture. And that way we can break up the workload. We can have these services developed independently. And clearly, if we want to change the implementation of how that service works, as long as we maintain the contract between the other services, then it really doesn't matter. So we can take a completely different approach. We can redeploy that and have that work in a better performant way, or doing something slightly different in terms of its implementation. And that's really the important thing. Plus, if we want to change the services, we can do that in a gradual way. We're not having to deploy the whole application in one go. We can take each individual service and deploy it as and when we have new functionality or new performance and so on. How we deploy our microservices is a very important consideration. If we look at the traditional way of how we would deploy applications, this is the kind of stack that we would be dealing with. At the bottom, we have our hardware. This is our bare metal server. We have processors, cores, we have memory, we have networking, we have storage, and so on. What we then do is we put an operating system on top of that. That provides an abstraction layer so that from the application's point of view, it doesn't need to worry about how to actually interact with the software. It uses a series of system calls to say, I want to open this particular file, I want to read from this file, I want to write to this file, I want to change things in terms of the properties of that file. But it's all done through this abstraction layer of the operating system through system calls. What we then do is we put on top of that the necessary software that we require to support the application, libraries and runtimes. Obviously, if we're dealing with Java, the Java runtime is the Java virtual machine, and we have a set of core class libraries which are provided as part of the JDK. So that could be an example of our libraries and runtime. We then deploy our applications on top of that, using the JVM, using the standard class libraries, and we run our applications. And if we want to run multiple applications, they're all going to run on the same physical hardware using a single instance of the operating system. So this is the simplest way that we can deploy applications, and it's the way that we've done in the past. What we've seen is as hardware becomes more powerful, as machines become bigger, and they have more processors and more memory, we want to be able to divide up that hardware in a way so that each application can be run independently of other applications. And the way that that has been done a lot in the past is through the idea of virtualization. And we've seen lots of different ways of doing that. But what that does is it says, okay, let's take the hardware, keep the host operating system, which abstracts away the issues of how to interact with the hardware, and then we add another layer on top of that, which is a hypervisor. The hypervisor allows us to virtualize the underlying machine in such a way that we can divide it up, so that we can virtualize a certain number of processors, a certain amount of memory, certain parts of the file system, and so on, so that we have certain parts of the disks that we have for storage. What we can then do is we can install guest operating systems on top of the hypervisor, and we can have multiple guest operating systems all using the same physical hardware, but very much independent of one another. So each operating system thinks that it has access to all of the hardware underneath through the hypervisor. It doesn't see any other guest operating systems, doesn't see any of the other libraries or runtimes in the other guest operating systems, and it doesn't see any of the applications in the other operating systems. So we can divide things up that way. The issue that we have with that is that whilst that works very well, it's actually quite heavy in terms of the load, because we've got, as you can see in the diagram, we've got multiple operating systems. We have the host operating system, and then we have guest operating systems. Every time we want to create a new virtual machine, we have to install the whole guest operating system another time. So there's no sharing of data between those. Isolation is great, but it also means that we can't share things in terms of the guest operating system. So that means there's a lot of data that needs to be stored on our storage. It also means that we have to provide a lot of facilities in terms of resources to run the guest operating system, in addition to running our applications. So this is where Docker comes in, and the idea of containers. What we do here is we take a slightly different approach. We still have the hardware, we still have the host operating system, but now rather than virtualizing the host operating system and the hardware so that we can deploy separate guest operating systems, we use a container engine. And the container engine allows us to isolate individual libraries and runtimes, services from one another, so that they don't have visibility of each other, and that way we can provide very clear line boundaries between them, so that if we're having support for multiple different clients on the same machine, there's no way that different clients can see each other's data. Also, the services can be restricted in terms of the amount of resources that they can use through the Docker container. We can restrict to a certain percentage of CPU, we can restrict to a certain number of cores, we can restrict to a certain amount of memory. And that is very important because it means that if one particular service has a problem, it has some sort of error in it, which means that it starts to use up more and more resources, if we didn't have that isolation, we would run into a problem where potentially one service could bring down all the other services that we're running on that hardware. By having the container engine limit the resources that are available to each service, if you get to a situation where one service has an error, it won't affect the other services. So it's contained within its container, from a resource point of view and doesn't have the ability to cause problems for other services running within the same host operating system. So this is designed to be lightweight. It's designed so that our services can be deployed with the minimum of requirements from the point of view of deployment. Obviously, the libraries and runtimes, the services themselves will require resources, but it's the idea that the container itself does not require a lot. You can spin up a lot of containers on a single machine and have those operate in a very lightweight way. And then, as I said, we ensure that we have isolation between the containers. And it's very important really to realize that when we talk about containers and Docker, what we're talking about here is isolation, not virtualization. It might look a bit like it's virtualization, and we'll talk more about that in a moment, but it's not virtualization. It is most definitely isolation. So let's look in a bit more detail at the way that the Docker architecture works. When I started looking at Docker, I understood the ideas behind this, which is that you can create a container which has all of the software that you need to run your application. And that can be deployed anywhere you like in such a way that the container carries everything that your application needs to run. So that's a very nice idea, because it means that you can just take your container, you can deploy it anywhere you like, and you don't have to worry about any configuration for the application. You don't have to worry about, do I need this particular level of the operating system? Do I need this particular level of the Java virtual machine? Do I need this particular level of a particular library? All of that is bundled into the container. But it was difficult for me to understand exactly how that worked. So I kind of dug into this, and I've created this sort of diagram which hopefully will help you to understand how Docker works. So what we've got is the same basic low-level things. We've got our hardware and we've got our host operating system. And in the sense of that, we're talking about the kernel. So the kernel is the thing which, as I said, abstracts away the hardware from the software. If we want to interact with that, we use the system call interface. And in Linux, there are a number of well-defined system calls. So there are things like open, close, read, write. There are more obscure ones like ioctl, which is IO control. But there are lots of system calls that can be used to interact with the Linux kernel and therefore with the hardware. So the Docker Container Engine uses those system calls. That's the level of abstraction that is used here. So we're using all of the Linux system calls as our way of saying this is how we can make things independent. We know which system calls are available for a particular version of the Docker Container Engine. So Docker Container Engines are sort of joined, if you like, or paired with particular versions of the kernel. So we know that the system calls that we require are available in those versions of the kernel. On top of that, we build a number of layers. And the layers that we put on top of that are the things that are required to build the container for our application. So we could start with an operating system layer. So in this case, we're going to use Ubuntu. We may be running Red Hat in our host operating system. We may be running Ubuntu in our host operating system, but it doesn't matter. The idea is that we are building a container which has a fixed configuration. So we want to say, right, we are going to use Ubuntu because we know where all the files are in Ubuntu. We know the way that's configured for our application. Ubuntu will use the Docker Container Engine and the system call interface to talk to the hardware through the host operating system kernel. So this is where we get our level of abstraction, is through the use of the system call interface. So we put our Ubuntu operating system into the first layer. What we then do is we put another layer on top of that. So we have a layer which contains our Java runtime, standard Java virtual machine, class libraries, and so on. We then might have another layer on top of that, which is where we need to use Tomcat. So we're going to have an application which is being, or a service which is being accessed through the web. So we'll use Tomcat as a servlet engine using the JRE on top of the operating system. And then we'll add a fourth layer on top of that, which is going to be the servlets that we require to implement this service. Now, the important thing here is that all of these layers are ones that are, in effect, making up our image. And the key thing here is that all of these layers are read-only. What that means is that we can share those layers between multiple containers. So we create an image, which in this case uses the Ubuntu operating system, uses Java runtime, uses Tomcat, uses servlets, all of which are read-only, so they're shared. It means we don't have to have, for every container that's going to use this set of layers, we don't have to have a duplicate of the Ubuntu operating system, of the JRE, of Tomcat, of the servlets. We have one instance on our Docker container engine on our host operating system. These are read-only. Okay, so obviously you're going to think to yourself, well, how does that work? Because surely we may be running a service which needs to make some changes. Okay, so what we then do is we add a writable layer on top of those layers which make up the image. So this is where we can make changes, and the writable layer will reflect the changes that we want to make to any part of the system. So if we wanted to, say for example, change one of the Tomcat configuration files, we could do that through our writable layer, because the application that's running on top of that would see the file system through the writable layer. The writable layer will intercept any calls to the file system so that it will say, this one contains a change. So rather than using the read-only version, it will use the changed version. So it only needs to record changes that you make to the underlying read-only layers. And that's really the kind of key thing here. We have a single instance of each layer, read-only, so we don't have to duplicate those. And the only changes that we need to record in terms of the writable layer are changes to those underlying layers. And this is using what's called copy on write. So we'll copy blocks of the layers as we need them, make the modifications to them, and then when application code wants to use those files, it goes through the writable layer. The writable layer will figure out, this is a block that has been changed, so it uses that one rather than the read-only version underneath. Putting that image together with the writable layer is what makes up a container. So we can use images to define the software that we want in our container, and then the container has this writable layer so that when the application runs, it has the ability to make changes in the file system without affecting the read-only parts of the layers. Now, Docker uses a number of things in terms of the operating system to implement what we've just described. So there's two big things. There's namespaces and C groups. Obviously, as I said, the primary layer is this idea of system calls that can be used by the container to access the underlying operating system and therefore the underlying hardware. But in terms of managing the container from the point of view of allowing it to use certain resources but not others, this is where namespaces and C groups come in. Namespaces allow a container to see only certain processes, so you can restrict the view that the container has on the processes which are running in that particular machine. If you don't want other containers to be visible, you can restrict that. Mounted file systems can be made visible, so you could say, right, we have one particular client working on these particular containers, so these containers can see only these mounted file systems. Different client with different containers can see different mounted file systems. Similarly with networking, we may need to virtualize networking so that each container can have its own view of the network system and allow network traffic to flow independently so that it doesn't have the ability to see network traffic that's going to other containers. So again, this idea of isolation. C groups or control groups are about the lowest level of hardware, so the CPU and the memory. And again, what we can do there is we can restrict the amount of resources that are available to a container by saying we only want a certain number of cores to be used by this container, we only want it to use a certain percentage of the CPU that's available. And the C groups will enforce that restriction. Same thing with memory. You can limit how much memory a particular container has, and as we'll see in a moment, it's quite important, the control group will restrict the access from that container to the memory. So it will only be able to use a certain amount of memory. Right, so we talked about Docker, we talked about microservices. Let's now talk about how Java works with microservices and some of the things you need to be aware of there. There are a number of different ways of creating Java microservices. There's three which have kind of become very popular recently. One is Spring Boot, the other is Drop Wizard, and the last one is Wildfly, Swarm. The idea there is that what you're doing is you're building a single self-contained jar file which has everything in it that you need to run the particular bit of the application or particular service that you're doing. This is about simplifying the way things are deployed so that you don't have to think to yourself, right, okay, I need to install Tomcat, I need to install this particular library, I need to install that particular library. What happens is you say, okay, I've got a container which has a particular operating system, I can then put a JRE in there. Everything else will be put into a single jar file that can be run on top of that. And it makes life very simple. So Spring Boot uses Tomcat, Drop Wizard uses Jetty as the underlying sort of engine for supporting web interaction. All about being very self-sufficient. All of the libraries, all the frameworks are bundled, which means you can test your application in isolation using all of those libraries, and you can know that when you deploy that, you can actually deploy it into the cloud using a Docker container, and everything has been tested together. You've got all the components that you need to do that. Does make the jar slightly bigger, but you have no compatibility issues. So it's not a problem in terms of size. It does make it a little bit bigger than if you have separate. So if you wanted to run separate services in the same container, then you could separate things out and have a number of have libraries shared between different services. But the idea with microservices is really do one thing and do it well. So this is the idea. You put everything in a single jar file, you deploy that in a single container. In terms of the advantages of using a container, one of the things is it isolates JVMs from each other. So you can have JVMs running inside a container, completely isolated from other JVMs running in different containers. The nice thing about that is you don't get confusion over which libraries are being used, which version of the JVM. It's all very self-contained. Does give you also a consistent deployment model. So Docker is designed for use with things other than Java. You can have C, C++, you can have Python, anything you want to deploy into a Docker container that will run on a machine can be deployed into a container. So by using this deployment model, it does give you a consistent way of doing things. So if parts of your system are using Java, parts of your system using C++, then you can use a consistent deployment model across all of those services and not have to worry about, okay, I need to do this thing with Java, I need to do this thing with C++, and so on. Right, now, one of the things you need to be aware of is that the JVM is not C group aware. What does this mean? Well, I set up a system where I have a box with 64 gigabytes of memory, and I configured a container to only be able to use 512 megabytes of memory. Fine. So what that means is that when we use that container and we run a Java application in there, it won't be able to use more than 512 megabytes of memory. Right. But what happens is that the Java virtual machine will ask the operating system how much memory is available in the system. And the way that it will ask it is in such a way that it will not get back how much memory is allocated to the C group in which it's running. It will get back how much memory is in the entire machine. So the answer that the JVM gets when we run it, in this case, is 64 gigabytes, not 512 megabytes. If you use something like Hotspot and you don't specify a heap size, it will use ergonomics and, in this case, would allocate a heap size of 1 gigabyte. If we run an application here, and I created a little application that basically just filled up an array list to make it bigger and bigger to see what would happen if we went over 512 megabytes of memory, this is what happens. So we create a new array list, okay, it goes off and starts doing things, and then we see this killed. Okay, this is interesting because we're not seeing an out-of-memory exception, which is what you would normally see if you filled up the heap and you went over the amount of memory allocated. You would get an out-of-memory exception and you'd be able to say, oh, okay, we have a problem because we don't have enough memory. But in this case, we see just killed. We don't see an out-of-memory exception. What we then have to do is we have to look at dmessage outside of Docker. So we go to our main machine and we look at the output of dmessage, and what we'll find in here is a message which says that the C group is out of memory, and so the process has been killed. This is something you definitely need to be aware of, because clearly in terms of the JVM, it's saying, oh, there's 64 gigabytes available, I'll allocate 1 gigabyte to the heap. But when it tries to use beyond 512 megabytes of heap space, the JVM is denied, and therefore the process gets killed. So very important to be aware of that. So if you're creating a Java microservice and you're running it inside Docker, you need to make sure to set the heap size based on the size of the container, so that the container and the heap size that's set for the JVM match. So if we look at JVM configuration, as I said, we need to configure the memory explicitly so that we don't rely on the defaults, which could potentially get it wrong if it's looking at a larger memory size and doing either ergonomics or using a default size. You also need to make sure that you configure the number of CPUs, because again, the JVM is not C group aware. What will happen is it will ask the underlying operating system how many processors are available, and it will get the number for the whole machine, not for that particular C group. That means that when the common fault join pool is created, when the garbage collection threads are started up, though the numbers of those will be based on the number of processors and cores in the machine, not for the C group. You can set those explicitly in the command line, so there's this quite long option -djava.util.concurrent.faultjoinpool.common.parallelism, and that way you can again configure the number of threads that are going to be used for the common fault join pool to be the number of threads that you have available from the CPUs or cores that you've allocated to that particular C group. Another thing to bear in mind is that when you set up the container configuration, the memory requirement of that container is not the same as the JVM heap size. So if you set the JVM heap size to be like 512 megabytes, you do not want to set the container to have memory allocated to it of 512 megabytes, because yes, that is how much heap space can be used, but the JVM will also require memory to do things. The other parts of the system, if you're running Tomcat, things like that, will require memory to do things natively, and the operating system itself will require memory to do things. So you need to make sure that when you set the configuration for the container, you add something to the heap size that you've allocated to your JVM in order that you don't run out of memory again that way. What are the challenges for the JVM when we're dealing with microservices? Well, the first thing is how to maintain responsiveness under load. This is important because obviously as you start to add more services and you start to have a higher load on your machine, then you need to make sure that the system will respond in the times that you want. And the problem that you have here is that often you will agree a service level agreement with your clients based on the entire application. But within that application, because you have a number of different services, you have in effect service level agreements between the services, which could be quite different to the service level agreement that you have for the end user. You know, it could be that certain services need to respond far more quickly in order for the overall response time to a user to be within a certain range. So this is something that clearly needs to be configured and understood when you're dealing with a JVM. You know, there are things like garbage collection that kick in, which can cause problems from the point of view of maintaining the latency that you have associated with your particular service, and we'll talk more about that in a moment. Also, how do we support multiple JVMs on the same physical hardware? How do we make the efficient use of resources? Do we have a number of services running and we tune those for the peak load, or do we look at the normal load? Because, of course, if we tune everything to peak load, what we're effectively saying is all these services have to be tuned for a peak load, whereas normal load is probably going to be quite a lot smaller. But in effect, we're creating an overhead for each individual service, which is multiplied then by the number of services we have. If we had a whole application running monolithically, then we would build in overhead so that we could deal with peak load, which might be different to if we break it up into multiple services. So that's the kind of thing, again, that we need to consider when we're using JVMs. Also, how do we spin up services quickly? A lot of the ideas behind microservices is scalability, so that you can use a number of services to deal with increased load. You can just add more of that service and redirect requests from the client to other instances of that service. To do that, we need to be able to spin up those services as quickly as possible so that we can adjust to changes in our load. And this is really the key to scalability. Right, so let's talk about Docker and Zing and what we can do in terms of solving some of these issues and addressing some of the needs of Java running as microservices. So the first thing is that Zing has a different way of doing memory management. We integrate our memory management directly with Linux. So we have a thing called ZST, which is the Zing System Tools. That resides on the host and also has an implementation that we put into the container. So there's one part, if we're running microservices, one part that goes on the host operating system, and there's also one part that needs to be installed in the container. What that allows us to do is to have a holistic view of the system from the point of view of memory. So our ZST will be able to see all of the different containers and their memory usage, and we'll be able to optimize things for the containers so that we can manage things and allocate memory as it's required to those containers. It also has the idea of elastic memory, and this is very much based on the idea of how we can have more resilience to increased load. We'll talk more about that in a moment. But it very much is suited to the idea of multi-tenancy. If you want to have multiple JVMs running on the same physical hardware, this approach to memory management does make life a lot simpler in terms of managing those multiple JVMs. And what we actually find is that the more or larger numbers of tenants improves the efficiency of this system. So one of the things that we have is the idea of contingency memory. When we install ZST on the host operating system, we will have a certain amount of memory that we will allocate for use by JVMs. Now, by default, that's 75% of the available memory, but you can change that if you want to. What we then allow is for the situation where people get the heap space wrong. So if you configure your virtual machine to run with a certain heap size, we can actually allow your virtual machine to continue running if you go beyond that heap size. So if we have some contingency memory available, can't guarantee it because obviously if there are multiple JVMs all using contingency memory at the same time, we may run out of contingency memory. But if we have contingency memory available, we'll actually let the system go beyond the maximum heap size so that it can continue running. It's much nicer to have your service continue running rather than throw an out of memory exception and stop abruptly, because then people have to get involved and they have to figure out how to restart things and how to make things work again. And your customers might get upset. So this prevents some of the ideas of out of memory exceptions. I mean, clearly we can't prevent all of those. You can get to a situation where you run out of contingency memory as well, and you will get an out of memory exception. But if it's a situation where you go just a bit beyond your heap space, we will let you continue running. If you do that, we will automatically trigger faster rates of garbage collection. the idea there is that if you are going beyond your heap space, then what we'll try to do is start doing garbage collection more quickly and try and bring things back into the normal bounds, so it goes down below the heap space that you've allocated. Obviously, you can look at the log messages, you can see what's going on, and you can say, okay, maybe I do need to allocate more space for the heap on this particular service because it is going outside of the normal bounds. The other thing that we do is change the way the garbage collector works. So we have, rather than using the traditional hotspot OpenJDK way of doing garbage collection, we have a thing called the C4 garbage collector, which is the continuous concurrently compacting collector. This is, again, very much designed to work in a multi-tenancy environment. Because the collector works with the Zing system tools, it does give much better memory management. The JVM doesn't hold on to memory in the sense of physical memory. It will actually return it to the underlying operating system, and that memory can be reused for other virtual machines. So if you've got multiple virtual machines, what's happening is that the physical memory is returned to the Zing system tools and can then be reused. This is very much different to the way things work with other JVMs. Certainly when you're doing allocation and you need a new thread local allocation block, which is what you use in the young generation, this will be allocated directly from the kernel. So it won't be taken from the heap space which is being used within that JVM. It comes directly from the kernel, and what that means is that you actually get better performance because we can use our Zing system tools to give you a block of memory which is in effect hot. So it's already in cache and it's available for use, and you'll get better performance from that rather than potentially using a block which is allocated but hasn't been used for a while, so it needs to then be brought in from memory and has all the overhead of the degradation and performance on that. So again, when you do garbage collection, it returns memory directly to the kernel rather than leaving it as allocated to the virtual machine. When you've got multiple JVMs running on the same physical hardware, this is very good in terms of performance. Now, one of the things that people often say when we talk about Zing is, oh, you need much bigger heaps, because we actually support heaps which go all the way up to 2 terabytes. So that's 2 terabytes of heap space. And people seem to think that because we support 2 terabytes of heap space that you need a bigger heap. And the reality is, no, you don't. So this is just a small example where I'd set up some benchmarking using Hazelcast on a 2-node system. The left-hand side of the graph is a non-Zing JVM. I'll leave you to figure out which JVM that is. And the one on the right is Zing. So what we can see here is that in terms of latency effects from garbage collection, we can see that on the left-hand side, we're getting fairly consistent pauses in the range of probably around 25 to 40 milliseconds, with a nice big spike there all the way up into sort of 230 milliseconds. And the graph at the bottom shows the latency by percentile, so how much, what percentage of the time you get a particular level of latency. If we look at the Zing graph, we'll see that it's pretty much flat. So we would actually have to change the scale on the graph to see that we were probably getting latency caused by garbage collection and underlying effects in the range of probably less than 10 milliseconds compared to the one on the right, the one on the left. And again, looking at the percentile distribution, we get a very, very flat graph in terms of that. And that's using a 1 gigabyte heap. So we're not talking about using tens, hundreds of gigabytes. This is a 1 gigabyte heap, and we get the same effect in terms of improving the efficiency regarding latency. The other thing, how do we deal with spinning up services? So the problem that Java has is that it is interpreted. So it's bytecodes, it's not native instructions. This is the whole idea of write once, run anywhere. What happens is that when you start your application, the application will run in interpreted mode. The bytecodes are taken, read, and then they have to be converted to the native instructions for the platform it's running on. Over time, the code will be analyzed, and hotspots within that code, where you execute certain methods in a loop a certain number of times, will be compiled into native instructions so that they don't have to be interpreted every time. And this is what we call a warm-up. So the application has to run for a certain length of time to allow the JIT compiler to analyze where the bits of code are, which are the ones that are being used most, so it can compile that code, have it as native instructions, and have it run at native speed. The problem is that when we restart our Java application, or if we're going to start up a new instance of our microservice, we have the same problem. We have to start off with our interpreted mode. We have to then build up through our warm-up phase and analyze the pieces of code that need to be compiled. Right. What we really want to do is to start our application, let it run for a certain amount of time, get up to speed, but then when we restart it, we want it to start at the same speed. We don't want to have to go through the warm-up phase every time. And that's essentially what one of the features that we have in Zing does. We have a thing called Ready Now. And what that does is it says, okay, let's let the application warm up, but then once we've got to a stable state where we know that the application is running in the way that we expect it to, we will record a profile. We'll record a profile of which methods have been compiled and which pieces of code are available and so on. When we start an application using Zing and using Ready Now, what we can do is we can load the profile when we restart. Now, because of the way that the JVM is designed and the way that the JVM specification enforces certain things about how classes must be loaded and how methods can be compiled and so on, we can't start immediately at the speed that you would expect. What we have to do is we load our profile and say, right, load all these classes, compile all these methods based on the profile that we've recorded, but do that straight away as the application starts, with the idea that we will get to the optimum level of performance very, very quickly. We don't have to go through this longer warm-up phase. We can do a lot of optimizations and get it going very quickly. We can also avoid some of the problems that affect applications in terms of de-optimizations by doing things this way. So there's some very nice things in terms of starting up small services very quickly and getting optimum levels of performance. Right, so if we want to use Zing with Docker, what do we need to do? Just go through this very quickly, but basically ensure that your host operating system is running version 5.15 or later of the Zing system tools. Then you want to start an instance of Docker. And in this case, what we're going to do is we're going to run an instance of Docker. We will set the path so that we'll include the version of Zing and the JDK when we install it so that it's available. We'll call our container Zing. We'll make it interactive so that we can use a terminal to communicate with it. We'll also allocate a sudo tty so that we can make it interactive. We need to map one of the files from the device directory from the underlying operating system into the container so that it will work. Again, this is how we do our memory management. So all we have to do is map the Zing MM0 device from the underlying operating system into the container. We then also want to simply bind a mounting point so that the temp directory from our operating system is available through the /Zing directory in our container. That makes it easier to copy files so that if we want access to things like the JVM and so on, then we can do it that way. We'll use Ubuntu 14.04 as our base image. I mean, you can use whatever you like, but in this example I was using Ubuntu, and then we'll execute the bash command. Once we've done that, we need to start up our container, have that running, and then we need to install the Zing system tools inside that. So we simply use dpackage, and we use the version of the Zing system tools which is specifically for the container. So it's got for container in the name of it, and that will install the necessary parts for the container that will interact with the Zing system tools on the host operating system. Check version using Zing PS -v. That will report the version of the host. So this is useful because it will enable you to check that you have got the right version running on the host as well as on the container. Then all you have to do is install the Zing virtual machine, which is just again using dpackage, install that from the Debian archive, and then that will enable you to run the Zing JVM. And then, as I say, set the XMX as required for the running JVM. So that will set the heap size. Remember, it's not the same size as the amount of memory you've given to the C group, which you're running in. You need to set the C group to have more memory than the size of the heap there. And what we do there is we use the Zing system tools reserve on launch. So again, this is the way that we can manage memory more efficiently when we're using containers and microservices in order to allow better use of the resources in the machine. So just to conclude, microservices are very well suited to modern software development. I mean, this is this whole idea of agile methodology, being able to roll out changes as soon as they're ready rather than having to wait for big releases. It's about continuous integration, continuous deployment. Java microservices are different to normal applications. If you're going to do scaling by spinning up services as you need them, then speed of startup is going to be an issue. So, as I said, with Ready Now, avoiding the problem of having a warm-up of your application. Things like CPU, things like memory configuration, you need to be careful about how you do that within microservices and the container because of the issues that I explained about the JVM not being C group aware. Docker does provide very nice isolation of JVMs and services so that you don't have to worry about things bumping into each other. You can simply package everything into a container and deploy it onto whatever machine you want to in the cloud or on your own hardware, whatever. Zing is ideal for Java microservices. As I explained, we have different ways of doing heap management in terms of garbage collection, allocation, the integration with the Zing system tools. This works from small heaps to very, very big heaps. As I said, you can run with 1 gigabyte, that's no problem. You can run with 2 terabytes, that's no problem as well. And in terms of fast startup, Ready Now is the technology we have which addresses the needs of that. If you're interested in Zing, we have a free trial, so you can get a free 21-day evaluation license from this web address here, so info.azure.com, zingtrial.html. And what you can do is you can simply drop in the JVM and say, right, try my application with this. You install the Zing system tools, simply drop in the JVM. It's exactly the same in terms of the way that you start up your application. You probably actually need less command line options because in terms of garbage collection tuning, you literally start off by setting the size of your heap. That's it. There's none of this other configuration that you need with other virtual machines. So with that, I've got about 5 minutes left. I'm going to move over and see whether anybody has asked me any questions. Let's see whether there are some questions here. So let's have a look. Right, okay. So very interesting presentation. Will the slides be available afterwards? And the answer to that is yes. I will put them on SlideShare, and I will make sure that everybody who registered for the webinar gets the link for that. Okay, second question. Zing, let me just undock that. There we go. Yes. Right, so second question. Zing C4 does not hold empty free memory. What is the effect on application performance overhead with respect every time the allocation free happens, since it translates to kernel level operation? Well, yeah, it doesn't hold free memory because we in effect, because we're controlling the memory management, we can control the link between the virtual memory address space that's used by the JVM and the physical memory that's used underneath. So all we're doing is we're saying that for the JVM, we will reclaim the physical memory independently of the way that the JVM works. There's some quite complex stuff that we do in terms of the way that the garbage collector works from the point of view of what we call quick release. So we're able to release the page of physical memory from the virtual memory because we guarantee that the data that's in that virtual address space is no longer used. And so we're able to do that because we control both the virtual machine garbage collection and also the underlying way that the system works. So from a application performance point of view, it actually makes things better because one thing is that when we do garbage collection, we can actually allow the heap space to be very, very full before we run garbage collection. Because when we free up one block because we're doing some compaction, we can do what's called hand-over-hand compaction. And so we're able to use only a very small amount of memory to do the compaction physically. So yeah, it doesn't. It actually makes the performance of your application better because we can get better cache affinity and things like that as well. Next question. The record profile is specific on the kernel host operating system. So if we restart the application on another host, does it work? Well, yes, obviously it would. Yes, you see, because it's not the profile is about the code which has been compiled by the JVM. So it's not tied specifically to the operating system. What we do is we record the information about which classes are loaded and which methods have been compiled. We don't record like a dump of the memory, in which case it would be specific to a particular architecture and particular operating system. We can't do that because it's not allowed by the JVM specification. What we do is record the profile so that when the JVM starts up again, and you can start it up on a different operating system, a different configuration, then we can recompile the necessary methods, we can reload the classes straight away in order to give better performance on that. So it does deal with the fact of moving it from one platform to another. There may be some issues if you've got different amounts of resources available. It might you might need to test that a little bit more, but in theory it's not an issue from the point of view of moving it to a different platform. Okay, next one. My question is about licensing. I found that to be able to run Zing, I need a set container network type to host. Fortunately, this limits the usage of the container, e.g. I cannot use Docker, Compose, and also Amazon ECS services limits deployment options. Is there any way to use Zing with bridged network mode? I must admit I don't know the answer to that question. So what I will do is I will find out from the people who do know the answer on how our licensing works in that particular instance, and I will get an answer to you for that. I'll make it available to everybody if they want it as well. And then, very interesting presentation. Can Zing run frameworks that use runtime bytecode generation, e.g. Play, AOP frameworks, etc.? Yes, because in essence, Zing is doing exactly the same thing that the other JVMs are doing. From the point of view of garbage collection, it's a bit different. From the point of view of some of our underlying ways that we do compilation is a bit different. But in terms of its interfaces and the definition of those interfaces, it works exactly the same way. So it supports the full JVM specification, it supports the full Java language specification. Everything works in exactly the same way as it would with any other JVM. We run it through all of the TCK. We make sure that all of the tests pass. So it is a fully conformant JVM, absolutely no difference to any other JVM which implements the Java SE specification. So yes, the answer to that is that everything that will work with other JVMs will work with ours. Okay, so that is pretty much the top of the hour. So I'm going to end the webinar now. Looks like people did enjoy it, so thank you very much.